Okay, so it will start recording. Uh, right. So this is what we were doing. Let me quickly review it for benefit of people who are probably not here last time. We started talking about the two-view geometry, and so this is the geometry of the imaging process, I said, which occurs when you have two views of the same object. Okay, so possibly you're taking it with two cameras or the same camera at different positions, in which case the camera matrix will change. Okay. So the assumption or the notations should be noted because we will be using this throughout the notes. So you have a scene point capital X, and the cameras will be denoted by C and C prime. Okay. So this is capital C can stand for camera as well as camera center. Okay. So we will always assume that what the camera is placed at the camera center. Okay. So that is the reason why we can use the notation C. Okay, so C and C prime are my two cameras. The point X is projected through the first camera at the point small x and through the second camera at the point small x prime. Okay, and so we know that there is a homography or there is a projection, not homography, there's a projection that takes capital X to small x and takes capital X to small x prime. Those uh, projections are called P, and this P is exactly what? P is the P and P prime will be camera matrices of C and C prime respectively, right? Will be camera matrices of C and C prime respectively. Correct. So once you have found this camera matrix, you know the projection from the world point to the image point. Okay. So now, what the two-view geometry deals with, I think last time I mentioned what are the various questions that are considered under this. Okay, so yeah, here there. So the correspondence geometry is what we will study in a bit detail, which is given an image point small x in one view. How is the corresponding point in the second view constrained? Okay, so what can you say about where the corresponding point will lie in the second image? Okay, so we will see that there is actually a nice relation between these 2 points. So if x is the uh, image point in the first image, then the corresponding image point in the second image will actually be given by a matrix multiplication with x. Okay, and that matrix will be called the fundamental matrix of the configuration. There are many other questions also that can be answered about two-view geometry. One is this question about so this first question is about point correspondence, right? Image point correspondences. The second question is about the camera themselves. So what happens if the camera moves? So if you have a set of corresponding points, xi and xi prime, okay, then can you say where the cameras themselves are situated? Or can you derive from those set of corresponding points the camera matrices of the two cameras? Okay, so that will also sort of answer this question about uh, is it that one camera has just moved from one place to the other? Okay, so once you know the camera matrix, those questions can be answered. Okay, and this third one is the reconstruction problem actually, that suppose you know correspondences and from them you now have calculated the camera matrices, can you actually reconstruct the scene point, the actual world point from this information? Okay, so this is the question that is asked in scene reconstruction. Okay, so in the context of this question, one should note that, see, when you take an image through some camera, then what you have lost is depth, right? The depth information is lost. Now the human brain is very well trained to get to infer depth perception or depth information from 2D images. And now you want to also have a mathematical model for doing the same thing. Okay, so such models are there. Okay, and it is called as depth estimation. Okay, and estimation is a very important problem in computer vision. Very well studied also. It's not new. It has been there for a long time. But I don't know how much we will be able to cover it. However, I have suggested it as one of the problems for the project. So if somebody takes this up, it will be quite nice. So depth estimation of given two cameras, given two views, the depth estimation is can be done. There is a clear mathematical way of doing it. However, nowadays people are also, or there are also algorithms for what is called as monocular depth estimation. That means you have just one image. From one image, can you estimate the depth? Okay, so that is called as monocular depth estimation. So if you do two view depth estimation or the general depth estimation, that is also good. Okay, you will get to learn a lot of things. And if you want to look at monocular, you will first have to understand the two view and then go on to monocular depth estimation, which is like the hot topic in the past few years. Okay. All right. So that is about reconstruction. Okay. Uh, and you might think that deep learning is the only hot thing in or only to go thing in computer vision, but that is not true. 3D reconstruction is the real thing. Okay, 3D reconstruction, scene reconstruction, that is the real thing in computer vision. Deep learning has gained popularity and momentum in the last 7-8 years. Okay, and there are many things that deep learning can do, but there are also many things that deep learning cannot do. Okay, so we will see as we go by. Yeah, so moving on. So coming to epipolar geometry, I have explained to you what is the setup. Okay, and in this setup, we have our cameras C, C prime in these two positions. Okay, and this is the scene point. And the important things to note here are that the scene point and these two camera centers can be thought of as being on the same plane. These are 3 points. So look at the plane passing through these 3 points. Okay. Then, sorry, I'm getting all these notifications. I don't know how to switch them off. But try not to be disturbed by them. So look at this plane and well, the ray joining the camera center and the scene point, okay, that the image point lies exactly on that, correct? Similarly for the other image. And so actually you have that Cx, capital X, small x prime and C prime all are coplanar. Going ahead, the line joining the two camera centers, which is called the baseline, also lies on the same plane. Okay, and this baseline, the points at which it intersects the two images, those we said last time are called epipoles. These will also lie on that plane. Okay, so in fact, we have all these things, all the components in this image being coplanar. Which components? Camera centers, scene point, the corresponding image points, the epipoles, and the baseline. All these lie on the same plane. Okay, and so if you fix this, if you fix your scene point and hence the plane pi, then you will have a homography from image 1 to image 2, right? So homographies, which we already saw last time, you can have homography. So you have homography that maps x to x prime, and that homography we will term as h prime, h pi. Okay, pi because it is corresponding to this plane pi. If the scene point changes, okay, the plane is going to change, and hence the homography is going to change. Okay, everything changes. Another thing that is important in this configuration is that, well, if you fix this scene point and hence if you fix this image point, okay, and with respect to image point, the question to be asked is which points here are going to correspond to this point x. Okay, so which points in the second image correspond to this point x? Are there many candidates or are there few candidates that you need to look at? So one thing is clear that if x is the image point of capital X, so you're looking at this array, right? And now x prime is going to be the intersection of this ray here. So it's like the back projection of small x projected onto the second camera. That intersection point is this x prime. Okay. Now this entire ray projects on the point small x. So all these points on the ray are mapped here. Now all these points on the ray could be mapped to different points in the second image. Okay. So to check exactly what is the point corresponding to x, you need to look at all these candidates. Okay. Now here it is quite clear that this is the point, but otherwise these are all the points that correspond to points on this ray. Okay, and we have drawn it only till here, but of course this line can extend, or this ray can extend, and then this will also extend. Okay, so you have this actually epipolar line for x, that's what this is called, and the piece of that line between e prime and x prime, that is the segment that that corresponds to points between x and the scene point capital X. Okay, so this corresponds to this. This is just similarity. Okay, so this piece also sometimes is called the epipolar line for x. Okay, so given an image point x in the first image, the points that correspond to the ray mapping to x are points on this epipolar line with respect to the second camera. Similarly, you have the symmetric situation where you could be talking about x prime and the epipolar line for x prime, and that's going to be here. Okay, and the epipole here is denoted by E. Okay, so this notation is fixed, E. Okay, E is the epipole and E prime is the second epipole. Also, I told you that when we are talking about this configuration, we will usually term the camera on the left as the first camera, or the left camera, or the reference camera. Okay, and the camera on the right as the second or right camera. Okay, and sometimes later on we will also assume that this reference camera is centered at the origin of the world coordinate system. Okay, so that will make the camera matrix for this very simple looking. Okay, and then we will have some general camera matrix for C prime. So those are some simplifications we will be doing soon. Okay, so this is the situation, and then I had listed down all this terminology properly last time, and we looked at a few examples. So I'll not go through all that in so much detail. Let me come to the point. Yeah, so the first question about correspondence geometry was, given x, how is x prime constrained? Okay, so geometrically we see that you back project this and then you get this epipolar line. Okay, and now we want to get an algebraic formulation of the whole thing, which means if you are given x in the first image, then what can you say about x prime? Okay, so that is the question. So for each point x in the first image, there will be a corresponding epipolar line, and that epipolar line we will denote by small l prime. Okay, so that's our notation. And geometrically, I just told you how to construct the whole thing. Okay, and we want to. I think this is where we were when the last meeting was ended. So I think I had talked about this homography between x and x prime. Okay, and then to construct this L prime. Okay, what you have to do is just take so now you know this epipole. Okay, and this homography will give you this x prime, right? H pi applied to x will give you this x prime. So once you have x prime and E prime, then you know that the epipolar line corresponding to x is the line that passes through these 2 points. So this L prime is just the cross product of x prime and E prime, right? So that gives you the formula for L prime. So L prime is E prime cross x prime. Okay. Of course, the order doesn't matter here because everything is in homogeneous coordinates. Okay, so we don't care about that multiplication by -1. So now moving on, this is E prime cross. Well, x prime is H pi x. Okay, we will show that this cross product with E prime can be all actually thought of as a matrix multiplication. Okay, I will shortly show that. So this cross product will be some matrix multiplied by this matrix H pi, and that is collected together in this matrix F, which is called the fundamental matrix. Okay, so that is the sort of geometric explanation of the whole thing. And now let's do the derivation properly. Okay. Okay, so here, yeah, I think there was also one more piece of terminology that I introduced, is that so this blue lines here and the blue points correspond to images of one scene point capital X in the two cameras. Okay, so you could have another point, say, so this is say x1. Okay, so another point x2, and the green lines correspond to that. But the important thing to note is that all these epipolar lines, okay, so for various points in the image, you will have various epipolar lines here. Okay, but all those epipolar lines will pass through the epipole. Okay, and the set of all these lines that will pass through the epipole for a fixed pi, this is a pencil of epipole. This is called a pencil. Okay, it's a family of lines passing through E. Okay, so it's called a pencil. And I think at some point I had also shown you, yeah, this image where, you know, when your scene point moves, we noted that the plane will move, correct? The plane with respect to which you are working. And so since all these epipolar lines are going to pass through the epipole, the planes are also going to pass through the epipole. And so you'll have a family of planes like this. When your X changes, your plane will change, but they will all pass through the baseline. Okay, so that family of planes is also called pencil of planes passing through E or passing through the baseline. Okay, so that is language. Yes, and the important point to note here is that what is going to happen is you're going to have a map F after all this process. What you're doing is you're taking our image point X here, and you're ending up with an epipolar line here. Okay, so a point means you are going, so this is going to be a map from P2 to P1. Okay, P2, you're going to pick up a point in this projective plane, and you're going to give me a line, which means P1. Okay, so the rank of F is going to be 2. Okay, so this will be some 3 by 3 matrix of rank 2. Okay, so this we can see even geometrically this way. Okay, and this is going to be important, which, because rank of F is 2 means that F is going to have a non-zero null vector. Okay, and which will be useful later on. Okay, so this is just a small remark that the rank of this fundamental matrix that we will compute will have rank 2. Okay, okay, here goes the algebraic derivation. So let's notice that if you want to I think I've written something around here. I should be just saying that to obtain small x from C and P. So C means camera. So camera means also the camera matrix. Okay, and X is the scene point. Okay. So to obtain small x from the given camera and the scene point, you just use this projection. Small x equal to px, correct? This we already know. Now what we want to do in the geometric motivation was that you want to back project this point x, reach the point capital X, and then project it through the second camera, correct? Now to do this back projection, what you want to do is invert this process, correct? So inversion, but this is not a square matrix, or if you don't know this is invertible or whatever, okay? So inversion will be done using a pseudo inverse. Okay, so for that what we'll do is so back projection of this point will give you not one point but a ray. correct? Because all those points were mapping onto the small point, small x. So this is how you can back project. So you will get a one parameter family of points xt equal to p plus x plus tc. Okay, so a linear combination of the pseudo inverse of small x, sorry, uh, small x plus tc. Okay, so you will have this one parameter family of points. When t is equal to 0, what do you get? When t is equal to 0, you are at the image point x naught, image point x. Okay, and when t is infinity, okay, then we sort of say that we have the camera center C. Okay, so at infinity we have the camera center, and sorry, again there is some. So x0 is p plus x, which we want it to be the scene point. Okay, so this is capital X. Okay, so this will be our, this is actually convention. Okay, so x0 will be actually our capital X, okay, which is p plus x, that is the scene point. And at t equal to 0, we will say that we have the camera center. Okay, so that is, yeah, this picture is better. So you have p plus x here. Okay, so this is exactly what will denote the back projection of small x through c. And this c will be thought of as what you get when you take t to infinity. Okay. All right. So now you did back projection, and now you want to project it through the second camera. Okay. So you simply apply p prime to this p plus x, and that will be your x prime. Okay, the image point through the second camera. So that's what I have written here. So you have, and then we saw that we have this epipole, which I have not drawn here. Sorry. So this is the camera center and this. So there is the point where this line segment meets. Okay, this is our epipole E prime, correct? So this the segment joining these two, or the line which passes through both these points, is the required line L prime. So L prime is going to be now P prime P plus X cross E prime. But what is E prime? E prime is the projection of this camera center C, is the projection of C through the second camera. Okay, but the projection of any point through the second camera is given by P prime applied to that point. Okay, so the epipole E prime is P prime C. Okay, and this is true in general. Also, so you should note that epipoles will always be given like this. E prime will be P prime applied to the first camera center, and E will be P applied to the second camera center, because the reverse relation is also true. Okay, so this way, if you know the camera, which means you know camera center and the camera matrix for both cameras, then you can find both epipoles. Okay, that's what this formula is saying. Okay, so coming back to the earlier computation. So L prime is P prime C cross P prime P plus X. Okay, so P prime C is this, so I'm going to replace it by the notation E prime again, where E prime is the epipole. Okay, so now what we want to see is this cross product. Okay, that this cross product can be written as a matrix. That's what I'm going to try and show. So suppose E prime is this vector Ex prime, Ey prime, Ez prime. Okay, and for simplicity, I'm going to replace all this by x prime, and x prime I'm going to take it to be the vector ABC, AB lambda. Okay, where lambda is a scalar. This is a vector in P2. So look at the cross product, E prime cross x prime. So it is just this matrix whose determinant, oh, I should say determinant of this. So it comes out, so if you calculated, it's going to be written in vector form. The components will come out to be these three, right? You can quickly check. The component for I will be lambda Ey prime minus B Ez prime and so on. Okay, so these three components are what come out as the cross product. Okay, so now these three components can be rewritten as a matrix product in this way. Okay, so look at the first component is lambda Ey prime minus B Ez prime, correct? So what I can think of this as, I can think of this as 0 minus Ez prime Ey prime applied to AB lambda, right? If I do this if I do this multiplication, the first row by this column, then I am going to get exactly this first component. Okay, similarly for the second and third components. So the point now is that this cross product with E prime, I'm expressing as this matrix multiplied with X prime, correct? So E prime cross X prime is this matrix applied to X prime. Okay, so what we will do is, so this is something we'll be using all the time from now on. Okay, that the cross product is actually expressible as a matrix multiplication. So this matrix we will denote by, have I written it here? Yeah. So the cross product can be expressed as this left matrix multiplication, and we will denote it by E prime cross. Okay. So the notation E prime cross will mean that, so if I'm applying E prime cross to some vector t, or if I'm multiplying it with some vector m, then it will mean that I'm taking this matrix corresponding to cross product with E prime and then multiplying it with whatever vector or matrix that comes later. Okay, so that is going to be the notation from now on. Okay, so E prime x is this notation. Okay, so always this is going to be a vector. When this is a vector, this will make sense. Okay, so I hope the notation is clear. We will be using it freely from now on. So now what we want to notice is that P prime P plus is nothing but your homography from the first image to the other. Correct? So if you go back to this, okay, P prime P plus means you're sending small x. You're sending small x to capital X and projecting it through the second camera. That's exactly what this homography does. It maps x to x prime, right? So H pi is exactly P prime P plus. So now putting all this together, our L prime, which was E prime cross product X prime, will now be written as E prime cross product H pi X, and E prime cross product with this in the new notation is E prime cross H pi X. Okay. So this matrix E prime cross and this matrix H pi multiplied together give us some matrix which is capital F. Okay. So thus capital F is E prime cross H pi. Okay, so you can either think of it like this, or if you want to think of it in terms of the camera matrices, then it is E prime cross P prime times the pseudo inverse P plus. So here we have found the first sort of expression for the fundamental matrix. I'm saying first expression because there are many expressions for the fundamental matrix. Okay, so this is one of the simplest looking, and all it involves is, so what do you have here? You have the second camera matrix, you have the pseudo inverse of the first camera matrix, and you have the epipole, the second epipole, okay, or epipole in the second camera. So if you know these three things, then you can compute the fundamental matrix of the given configuration. Okay. Now, but information does not always come to you in this form. Okay, you could be given different sets of pieces of information from which you might want to compute the fundamental matrix. So it turns out that there are many different derivations for the fundamental matrix and many different expressions, which will all be equivalent in the end, but will help you compute F from different pieces of information. Okay, and now the most not most. For the second problem that I was talking about, where you are given point correspondences between two images and want to come up with the uh, camera configurations, which means P and P prime. In that situation, as well as in the scene reconstruction situation, if you are given point correspondences and you want to reconstruct the scene, the question comes down to computing this F. Okay, so so if you want to compute this F from point correspondences, there is an algorithm similar in I'm not saying similar exactly as in steps, but in similar in spirit to the direct linear transform that we saw for calculating homography. Okay, so then that is a different derivation of the fundamental matrix. Okay, so like this, there are many derivations. I don't know if we will have time to look at that one. Again, it will be nice if somebody does it in one of the class projects. Okay, or I can give you a reading assignments, not too difficult. Okay. Okay, any questions so far about the fundamental matrix? Let's see if we can quickly derive, some other expression which will also give you some more insight. Now, the thing to remember about the fundamental matrix is what it does. It takes a point from the first image and gives you the corresponding epipolar line in the second image. That's what the fundamental matrix does. Okay, so keep this in mind. You shouldn't forget what F does. Okay, so now here is another sort of derivation for F. Okay, so suppose you have the two cameras given to you as, so remember this camera matrix, right? In general, how a camera matrix is written as? So a general camera matrix is given by K, R, T, right? So what is K, R, T here? This is the intrinsic parameters. This is the rotation. This is the translation, right? This is a 3x3 matrix. Where you have your if you're writing this in pixel coordinates, then this is going to be alpha x, alpha y. There is a possible skew. There is the principal points px, py, 1, 0, 0, 0. That's what K looks like, right? The rotation matrix, well, is a rotation matrix. Okay, so it's some upper no, this is upper triangular. This is just a rotation unitary matrix. Okay, sorry. And then there is translation. And so this is why we are into homogeneous coordinates. Remember, you want to be able to express this whole thing as a matrix. So this is a sort of 3 by, don't know, yeah. So 3 by 4, 1, 2, 3. This is your rotation. And then these 3 points correspond to the translation. So this is a 3 by 4. Okay. So this is how the entire, so these are the extrinsic parameters or external parameters which describe the position of the camera in space. Okay, and these are the intrinsic parameters which describe, well, the principal points, q, focal length of the camera. Correct. So and also what you need to remember is that what are these R and T exactly? These R and T tell you exact. So if your world coordinate system has this as the origin, okay, and if your camera coordinate system has this as the origin, if this camera is here, then these R and T express exactly how or exactly the relation between the world origin and the camera origin. Okay, how do you get to C from O? That is, so you do some translation first and then you do a rotation, and that's how you will align the world coordinate system with the camera coordinate system. That's the information that R and T give. Okay, so all these things you have to keep in mind. This is all the information that is encapsulated in these camera matrices. So if you know camera matrices, you know everything about all these things about the camera. Okay. Then we have also seen that a general camera matrix can also be given to you just as a 3 by 4 matrix. Okay, just as an array of numbers like this. If it is calibrated, that means you know this split. Calibration means finding this split, okay, or finding all these parameters for any given 3 by 4 array of numbers. So your P could be either like this, or it could be calibrated and look like this. Okay, so of course you know how to go from a calibrated form to a general 3 by 4, just multiply out their elements. And we have also seen in that lecture about anatomy of a matrix, anatomy of the camera matrix, that if you are given a 3 by 4 array like this, how do you compute the components of this calibration? Okay, so for example, we know what should be the camera center, right? The camera center is exactly the null vector of P. Okay, so you can find the camera center given P like this. You can find that this T. Okay, there are many things that you can find from P. Okay, so so all these things just keep in mind. Okay, so to begin with, I'm looking at the simpler case where P is already given to us as a calibrated matrix. Okay, not like this. Okay, so that is what we are looking at right now. Okay, so the two cameras are given as P equal to Ki0 and P prime equal to K prime RT. Okay, what does this mean? K, okay, these are intrinsic parameters, whatever it's an upper triangular 3 by 3 matrix. I means what? I means I and 0. This means that the origin of the world coordinates, there is no translation. Origin of the world coordinates is the origin of the camera coordinates also. Okay, so the camera is centered at world origin. That is what this is saying. And there is no rotation. This is identity matrix. So this is saying that the camera axes are aligned with the world axis. Okay. So if you are, that is sort of the, for a reference camera, that is the best position. When in two view geometry, the best position for a reference camera or the easiest position is that the reference camera is at the world coordinates. Okay, which means there is no translation from world coordinates to camera coordinates. There is no rotation. Okay, and so your extrinsic parameters are exactly the same as world parameters. There is no change. And of course, but there could be some intrinsic. Okay, there is some focal length and so on. Okay, so this having a camera matrix like this means camera is located at origin of the world coordinate system and axes are aligned to world axis. Okay, and this is the general situation. So second camera, I don't know where it could be. It is at some other position, and so for that position we know R, T, and K prime. Okay, so we are given two cameras like this. These are calibrated cameras, so we know the split. Okay, so notice. So remember, we for this computation of f, we require three things, right? We require this epipole, which can be obtained as we saw before, that E prime is just the image of C in the second camera. So E prime is P prime of C. Okay. We require P prime and we require P plus. Well, P prime is given to us. Okay. We need to compute P plus, which means the pseudo inverse of P. If we can get these two, okay, it is easy to get this E prime also, because if you know P, then you also know the camera center of the first camera. It is the null vector of P. To that you apply P prime, you will get E prime. Okay. So getting this, getting E prime and getting P prime is not difficult. I mean, P prime is already given. It is P plus which you need to compute. Okay. So that's what we do. Okay. So notice that your P is Ki0. Okay. So if you multiply this out, okay, the first 3 by 3 part is going to be K itself and the fourth part is 0. Okay, this fourth column is 0. Okay, so the pseudo inverse of this is easy to compute. It is simply K, you put K inverse in the first place here and 0 transpose. So that's the pseudo inverse of P. Okay, so this advantage we get because we assume that P has this simple form. Okay, so this is P plus. And we know that E prime has to be P prime C. E prime is image of C prime in the second camera. So the question now is, what is C? But C is the null vector of P. Okay, so you can think of it either that way. It is the null vector of P. Okay, or you can think of it as, well, it is the world origin. No, this is what the information is telling us, that the camera center is the world center. World center is 0, 0, 0, 1 in homogeneous coordinates. Okay, so to this point you apply P prime, you will get E prime. Okay, so that's what I'm showing here. Okay, so K prime RT applied to C. So this expression is slightly being simplified here. So K prime R I have written here as a 3 by 3 matrix. K prime T is this column here, and 0, 0, 1. Okay, so now if you apply this 3 by 4 matrix to this vector, the only thing that's going to survive is this column. So this is K prime T. Okay, so E prime is K prime T. Okay, notice that you can also find E, the epipole in the first image. Okay, so this also you can find, and we don't require it here, but you can find in the similar way, because E is going to be P C prime, and C prime is going to be the null vector of P prime. So using that you can also compute E. Okay, so this, we have a formula for this we derived earlier, and so E will look like this. Okay, anyway, so coming back to F. So F, we know the formula is this. Now we have found all these components. Okay, we know E prime is K prime T. So E prime cross is K prime T cross. P prime is K prime R K prime T. Okay, and P plus this pseudo inverse is K inverse 0. Okay, and so I have just simplified this expression. Okay, this times this. So this is going to give me what? So K prime R, because of this 0 here, okay, this thing will vanish. So you are only left with this 3 by 3 times this 3 by 3. Okay, so K prime R K inverse. This is what you got, another expression like this for the fundamental matrix of F. Okay, so this is in terms of what? This is in terms of internal or intrinsic parameters of the two matrices and position of the first of the second matrix. This R and T describe the position of the second matrix. Okay, so with this input you can also find the fundamental matrix in this way. Now what we will do is, we will try to simplify this expression a little. So I have a few notes here. These are small lemmas which are very obvious about matrix operations only, that will simplify this operation for us. Okay, or it will give us, I shouldn't say simplify, it will just give us another expression. Okay, so in this expression, this cross or K prime T is on the left. Okay, or E prime is on the left. Then we can get another expression when this is, where this is on the right. Okay, so this is this set of two lemmas, which are actually nothing but some matrix algebra. And I think you can go through this by yourself sometime later. Okay, so this cof M is nothing but the matrix of cofactors of M. Okay, which, if you remember, is defined as the matrix which has, well, you know what cofactors of M are, right? So I won't spend time with this. And you know that the matrix is also given by determinant of M times M inverse transpose. This is actually what you use in 11th standard to calculate M inverse, right? So, so yeah, anyway, so what I want to say is that if you have X and Y being column vectors, okay, then one thing to observe is that Mx cross My can be thought of as the cofactor matrix of M applied to X cross Y. Okay, so this can be easily checked actually. So I think I have written something here, or maybe not. I don't remember. But anyway, this is something you can easily check. Okay, so Mx cross My is cofactor of M times X cross Y. So that's the first point. for what we want is that sort of a commutation relation. Okay, commutation. So we know these quantities. So here I have written some vector T cross some vector, some matrix M, some non-singular matrix M. I want to sort of see what happens if I want to change the order, or if I want this T to come to the other side, what changes should happen. Okay, so that is called as a commutation relation. These don't commute blankly. Like this is not that T cross M is M times T cross. That is not true. But we want a way of putting this on the other side. Okay, and that is what this little lemma is about. So it says that if you have some vector T and a non-singular matrix M, then T cross M, this product, can be written as M inverse transpose times, you look at the vector M inverse T cross, okay, the matrix corresponding to M inverse T. So this is sort of a commutation relation. If you want to start with T on the left and you want to put it on the right, then you have to make these changes. Okay. This is all up to scale, okay, because I mean, this could be multiplied by, this is actually multiplied by determinant M, and I'm getting rid of that determinant M. So I have written up to scale. Okay. So yeah, the point is we have this commutation relation for these matrices. Okay. And that is what we want to use. So using this lemma, if we, so here what we have in our expression is this matrix multiplied by this matrix, correct? So I have this in the same situation as that of the lemma. So now what I want to do is I want to take, I want to pass this matrix to the other side. So I'm going to apply lemma 2 over and over. First I will cross K prime, then I will cross R, then I will cross K inverse. Essentially that's what we are doing. So here, so this first step is crossing K. Sorry, K prime, I think. K prime, yeah. First step is called crossing K prime. Okay, so it can be crossed this way. So there isn't much, I mean, too much mathematics here. I'm just blindly applying this. Okay, so just follow the nose, apply this, you will get this. So that the earlier expression, now this has come here. Okay. Now this I want to move beyond R, so that will become like this. And now I want to move this matrix to the right of K inverse, and that will give me this last expression. Okay. And notice that E, the epipole in the first image, is P of C prime. Okay, C prime is camera center of second camera. Camera center of second camera is null vector of P prime, and we have seen earlier that the expression for that can be given this way. Okay, so this is something we have seen earlier. So P applied to this, and remember P was Ki0, correct? So that applied to this vector is exactly Kr transpose T. Okay, so this Kr transpose T actually can be replaced by E. Okay, so now we have two nice expressions for the fundamental matrix. One is with the epipole E prime on the left hand side like this. Okay, the other with the epipole E being on the right hand side like this. So what this is telling us, this is not only giving us sort of a commutation rule, okay, but this is also telling us that you can find f from either the epipole in the second image or the epipole in the first image. Okay, so you can use either of these pieces of information, and either of them are easy to derive once you know the camera matrices in calibrated form. Okay, so this, you can use this formulation if you know the camera matrices in the calibrated form. Okay, which was, I mean, we started off with this, you know, simple expression for the first camera, but there is a general way also of doing this. Okay, so as you can imagine, the formula will become a little more complicated. So if you understand the situation or you understand the expression when the first camera is so simple, then you know you can anytime you need, you can look up what it is when this is not as simple. Okay. Anyway, are there any questions about this derivation? Okay, so if there are no questions, well, you should probably go through all this once more. Okay, and but the point of this whole computation was that if you know the two calibrations or the calibrations of the two cameras, then you have nice expressions for the fundamental matrix in terms of elements in that calibration. Okay. Now what I want to do is list a few properties of the fundamental matrix. Okay. So one very important property is that the fundamental matrix, there is a equivalent condition. Okay, so we have this formula and derivation and everything, but there is a nice equivalent condition which is also stated many times as the definition of the fundamental matrix. Okay, so I will just write down that. So one, the fundamental matrix satisfies that for any pair of corresponding points x and x prime in the two images. So I'll just write it like this. Okay, x and x prime in the two images x prime transpose fx is 0. Okay, this is not difficult to prove at all. Okay, because if x, remember what are these the placings of all these. Okay, what is fx? Fx is exactly this L prime, right? The line passing through x prime and the epipole E prime. Okay, and we are simply saying that x prime t L prime is 0, but that is simply by virtue of the fact that x prime lies on L prime. Remember we did this in project. What does it mean for a point to lie on a line in projective coordinates, right? That time when we did those basics of projective geometry, this is what we saw. Saying that a point x lies on a line L is same as saying that x transpose L is 0, right? So we are not saying anything very new here, but this is a very useful and handy sort of formulation of a very important property of the fundamental matrix. Okay, and so this is also taken as the definition of the fundamental matrix. So since this is an defining property, defining. So how should I say? I want to say that we define f this way. Okay, so yeah, let me say it this way. This is also taken as the definition of the fundamental matrix. Okay, so we have the following definition. Suppose we have two images acquired by two cameras C and C prime, whose centers are different. Okay, they are not in the same spot. So two unequal cameras. Okay, that is distinct cameras. Let me say two distinct cameras, C and C prime. Then the fundamental matrix of the configuration of the configuration is the so all this I'm skipping details, is the unique 3 by 3 rank 2 we saw homogeneous matrix uh, that satisfies matrix F, that satisfies the property that X satisfies X prime transpose Fx is 0 for every pair of corresponding points. For every pair of corresponding points X and X prime. Okay, so this is how the fundamental matrix is defined, and we have seen how it is derived. Okay, then I think the only thing remaining is to see how many degrees of freedom F has. Okay, so first of all, this is a 3 by 3 homogeneous matrix. So any 3 by 3 homogeneous matrix has 8 degrees of freedom, right? Because you can put one of the elements to be 1. So it will have 8 degrees of freedom. But notice that this is a rank 2 matrix. Okay, so again that is going to take away 1 degree of freedom. Okay, so we can say that F has 7 degrees of freedom. Okay, so this information we will require later, or whenever you want to see how many pieces of or how many corresponding points do you require to compute F. Okay. Okay, so I think I can, yeah, so one more. Suppose L and L prime. So this second property comes in handy when you're doing computation. L and L prime are corresponding epipolar lines. So I hope you understand what I mean by corresponding epipolar lines. Means X and X prime are corresponding points, then they are epipolar lines in the two images. So they are corresponding epipolar lines. And K is some line, any line, not passing through the epipole E, not passing through E. Then with reference to this third line, you can relate L, F and L prime. Okay. Then L and L prime are related by L prime is equal to F. So actually this cross product. So Fk, look at the vector Fk cross L. Okay, and symmetrically L can be written as F transpose K prime cross L prime. Okay, yeah, before this I should have mentioned that whenever F is a fundamental matrix, then F transpose is also a fundamental matrix. Okay, so maybe I should have mentioned that before writing this property. So if F is a fundamental matrix, then F transpose is also a fundamental matrix. So this follows directly from the definition by just taking transposes on all sides, right? So you just take transposes everywhere. So if F is a map taking X in the first image and giving you L prime, the corresponding epipolar line in the second image, then F transpose will do the opposite. F transpose will take X prime in the second image and give the corresponding epipolar line in the first image. Okay, but since both F and F transpose will satisfy this definition, both are fundamental matrices. They do exactly opposite things. F transpose is also a fundamental matrix which maps points in the second image to their epipolar lines or to their corresponding epipolar lines in the first image. Lines in the first image. Okay, and then I can add this one back. Okay, so now if you have two corresponding epipolar lines and you have a third line which doesn't pass through the epipole, then you can use that third line to sort of give a relation between L and L prime. Okay, that's what this is saying. So to understand this, actually I have made a, so this should not be like this because F of K will like that will not make sense. So F times the matrix of this cross product, that will make sense, right? And similarly here, what will make sense is F transpose K prime. Yeah. Okay. So to see this is not too difficult to see. Consider this expression. What does this mean? So this is simply short for, or another way of expressing this cross product, right? But so if K and L are two lines in a plane, then their cross product in projective geometry, their cross product is nothing but the intersection line, intersection point, right? So this is intersection point of K and L. And see, this is where a projective geometry becomes useful. Now intersection point, you don't have to worry about these lines are parallel or not. Even if they are parallel, intersection point makes sense in projective geometry. Okay. So this is intersection point of K and L. Okay. Let's call it X. Okay. Now X lies on L. X lies on L. Okay. So therefore, if I look at this, so F applied to this, okay, is nothing but F applied to this X, right? So this thing is X, so it is Fx. But what is F applied to X? The fundamental matrix applied to X gives you the line L prime. Okay, and so we have the required expression. And symmetrically, you can show the other for F transpose. Okay, so that's this property. Okay, and now finally, what I want to talk about is this notion called essential matrix. Which means it is the essential matrix is essentially the fundamental matrix in a simplified situation. Okay, so the simplified situation is that when both cameras are canonical cameras. Okay, and canonical cameras mean, so if you have a camera KRT, okay, because you know this K, what you can do is, so this is a non-singular, Ks are going to be a non-singular matrix, right? You can take its inverse, and from this matrix, you can create, or you can look at the matrix K inverse KRT. Okay, so this is going to be identity RT. Okay, so if you have this camera C or this camera matrix P, you can convert it to this P bar, let's say. Okay, so what is the relation between this P and P bar? You have normalized the intrinsic parameters. The extrinsic parameters are the same. So the parameters that define the position of this camera in the world are not changing. What is changing is the internal parameters have been normalized. Okay, so this P bar is called the canonical camera corresponding to P. Okay, this is canonical camera corresponding to P, where the internal parameters have been normalized. So now if you have a situation where you're looking at two cameras, let me just say P and P prime, which are both canonical. Okay, so you have already normalized. So if P and P prime are canonical cameras, canonical cameras, then the corresponding fundamental matrix is called the essential matrix. Because it is in simplified form and some very nice properties come by because of that. Then the corresponding fundamental matrix is called the essential matrix. Okay, essential also because it is truly just talking about the positions of the cameras now. Okay, internal parameters of both cameras have been normalized, so they are not playing any role, and the whole thing is dependent only on the positioning of the two cameras. Okay, so this word essential also sort of makes sense here. Okay, so this is the definition of the essential matrix, and so I will stop for now, and on Thursday we will list the properties of this essential matrix. Okay, so some properties of fundamental matrices simplified in this special situation, and again because of this simplification there are some other nice properties that come by. So what I will do is, I had promised that I will not take too many lectures on this two-view geometry so that we can move on to image processing. So on Thursday, I will try to wrap up this topic. Okay, there are many interesting and many important things to be done here. Okay, especially in the reconstruction. So that at least two things. One is how to compute f. This we did not talk about at all. Okay, so we have seen what f is, but how to compute f from a given set of correspondences. Okay, this process is called triangulation, and it is an extremely important idea. Okay, and it is assumed that you know triangulation if you have done a course in computer vision. Okay, so I will talk briefly about triangulation and this algorithm for computing f, and properties of the essential matrix. So these two things, and if time permits, I will talk a little bit about this reconstruction problem, but I don't know how much of depth we will be able to cover. However, I will assign some reading, non-graded reading assignment. So I will point you to the correct places to read if you want to learn a bit more about each of these topics. Okay. In particular, I will list out what we have not covered yet, which what is important. Okay. All right. So any questions for now? Okay. So if there are no questions, I will stop sharing. I just want to ask you if you have started working on the project. How many groups have started working on the project?
Ma'am, we have put up a project title on the sheet that you have shared, but our status is like not updated there. So we are not sure whether we'll be allowed to go with that specific project or we have to change it.
So have you listed some references? I saw something in Lie algebras and whatever.
Yes. So it's basically, we'll be working with this omnidirectional image. So a 3D object is there, and it is captured from all the possible direction. So it's basically like we are not working with a grid type image. Like images, most of the thing that we work, it's a grid type structure. So instead of that, we will be having this spherical image. So that is like the whole
point
idea
cloud.
Not the point cloud. You can think of it as like some 3D object is kept at like a sphere center, and whatever its image, it's projected on a sphere which encloses it. So so we will be using that spherical image, and we will do that. So in that case, what will happen is that even if you rotate the image, because it's a spherical image, so there should be rotation invariance. So that thing will come there. But in regular cases, like in CNN and stuff, we have this translation invariance that even if the object gets translated from position to B position, that does not it equivalently changes the representation. But in our case, we will have this rotation
with respect to rotation.
Yes. So because this is like a very recent stuff, and it's linked to some geometric deep learning. So this Lie algebra and all these things, these are just for the it is just used to come up what
so essentially you will be working with rotation matrices in R3.
Yeah, it's basically like doing the CNN stuff, but with like completely different geometries, not with the Euclidean geometry, but with the spherical geometry. Yeah.
So if you have a reference, put it up so that I can take one look.
Yeah. So ma'am, I have put up the paper there, as well as the people who have used this literature from signal processing to evaluate and calculate the convolutional stuff.
Okay, I'll take a look at it. Yeah, but it does sound interesting. And yeah, I do know that people are looking at this kind of rotational invariance for various situations. So yeah, I don't think there should be a problem. Just let me take one look at it. Okay.
Sure.
But you should, yeah. Otherwise, if you don't require any other mathematical baggage, I would say that yeah, definitely go ahead.
Not much, ma'am. Like little bit of signal processing and stuff, but I think I have studied that in my undergrad, so that shouldn't be an issue.
Signal processing is so anyway. We will also be looking at some Fourier transforms and things like that.
Yeah.
That is all you require.
Yes, ma'am. So in that case, I'll be working with like somewhat more general form of Fourier. I will not be working with that fast Fourier transform, because that is not possible to do on this spherical thing. So we have to like work with the most general form of the Fourier transform, and we'll do that. So in the paper actually, and the literature that I mentioned, it explains that how those things are derived.
Okay. Yeah. So if you are comfortable with whatever math is required, and if it is doable, that is the main point. It should be doable within whatever 2 months.
Yes, ma'am. I think the experiment, the GAN, unlike GANs and those things, experimentally speaking, it's not like very heavy thing. It's the training and those stuff like are quite straightforward. But just the thing is that we just have to like create our own convolution layer for that. That's the only thing.
Okay. Yeah. So if you think it's doable, I have no problem.
Okay, ma'am.
Yeah, I'll also take a look anyway. What about the others? Well, I'm just reminding you as courtesy. I mean, it is high time you start working on the project. A considerable portion of your grade is also based on it. And if you are running into problems, also it is your responsibility to talk to me about it. Okay, I will take a look at the spreadsheet again today to see what each group has chosen. But the last time I looked at it, like 2 3 days ago, a number of groups had still not chosen anything. So that's not a good sign. You have already registered for the course, so it is your responsibility now to make sure that you do the work in there. Okay, so if anybody has questions for me, I'll answer it, or we can end the meeting. Okay, no questions. All right, so then I'll see you on Thursday. Bye.